Alright, welcome back. Let's keep on trucking with our sets slides. So we learned a lot last time. Of course there's more notation. This is like, people have used sets to define all of mathematics, and so they made up a bunch of different things that like give them what they want to define what they need to define. So let's talk about this union and intersection stuff a little bit more. There's some more notation, but union joins together two sets, and intersection takes the stuff in common from two sets. You can do that to a lot of things at once, alright? So sometimes we want to like take a bunch of unions, take a bunch of intersections all at once. And mathematicians are notoriously very lazy. They don't want to write it out like this if they want to like take the union of a bunch of sets all together. So they made up more notation to save their writing. So instead of all this, A1 using union, A2 union all the way to AN, they did it this way. Union, all the AIs where I starts at 1 and goes to N. So it's like a, you know how, I'm sure you've seen this before, right? The summation notation, like start I at 1, it's like a mathematical for loop that adds stuff. It's like, this adds all the i's from 1 to n. This unions all the AIs from 1 to n. See that? That's the idea. So that's where they're going with that. It makes it a bit easier to think about some stuff. It's just like a mathematical for loop. So start I at 1, increase it until it's equal to n, and then just union all the AIs into one big set all at the same time. And they did the same idea for intersections. You want to intersect all these different sets? Well, and the sets are labeled like this. They're all the AIs, where I is from 1 to n, intersect them all into one final, I guess, smallest set, because intersection usually makes things smaller, because it picks out the common stuff. So with that in mind, here's a fun idea. So let's pretend that AI, the set AI, is this. It's the set containing I and 2i, so it's defined in terms of what it's got in it. So like A7, for example, that's equal to the set containing 7, right? And then also 14, 2 times that I. See that? So what's this? What's the union of all these guys? Can you figure it out? Well, first of all, this is implying that I starts at 1. It's unioning A1 with A2 all the way to A3. Alright, does that make sense? And so that's equal to, well, what's A1? Well, it's 1 and 2 times 1. 1 and 2, comma, 2 and 4, comma, 3 and 6. Okay, that seems nice. That's working out all right. And then how do you bring them together? Sorry, I put commas instead of the union symbol. All those things, all those smaller sets union together. Okay, so you just take all the things that they have and list them just once, because duplicates don't matter. So it's 1 and 2 and 3 and then 4 and 6. Okay, that's the idea. So that's the final answer there. Does that make sense? Hopefully it does. Do yell at me if you have any questions about this stuff. So let's see, there's some more operations like union and intersection. There's one called difference. There's like subtraction on sets. It's pretty, it's essentially what you would imagine subtraction is on sets. It's like, all right, take all the things in A and get rid of all the stuff in B. A minus B is every x such that x was in A and it's not in B. All right, so that's A minus B is all the stuff in A that's not in B. Okay. So, for example, if you got this, if A is 1, 2, 3 and B is 2, 3, 4, let's think about this. So A is 1, 2, 3, my favorite set, and then B is 2, 3, 4. Whee. Then their subtraction is all the things in A that aren't also in B, so we're chopping those guys off. So it's just 1. You see that? So this is going to be A subtract B, A minus B. Set difference going on there. So that's A minus B there. And let's see here. Yeah, let's see. So that's the subtraction. And then there's also this thing, that universal set, coming back to haunt us. So where did we first talk about that? It was very vague. And so now I can finally tell you a little bit more about it. So the universal set is just something implied by context, or somebody's giving it to you also. It's just a set in the background. All right. So let's say that somebody gave us that the universal set is U, like whatever it was. You can like negate a set. There's the ability for you to negate a set by creating what's called the complement, which is A bar. So A bar, the complement of a set A is like everything that wasn't in A, but was in the universe. Our universe of discourse is another way of saying that. So A bar is every element of the universe that wasn't in A. All right, so it's like A bar is equal to the universe minus A. It's all the stuff in U that's not in A. Okay, so let's say as an example, just to make this concrete, let A be the set of all the positive integers greater than 10. All right, so do you see how kind of from context, like the stuff we're talking about is positive integers, so that's the universal set. So somebody will usually give it to you as well if it's not obvious, but let A be the set of all the positive integers greater than 10. So do you see that A is equal to this set? Oops, I don't need rainbow anymore. So let's say that A is equal to the set containing like 11, 12, 13, all the way, right? All the positive integers greater than 10. So starting with 11. And then let's say that the universal set, like the domain of discourse, we say, is Z plus. It's all the positive integers. You see that? But we picked out a few of them and made it A. So now, with that in mind, what is A bar? What's the complement of A? What set is that? First of all, remember that Z plus is all the positive integers. It's 1, 2, 3, all the way to infinity. Boop. And so, A bar, it's all the stuff in the universe that wasn't in A. So universe minus A, which is like all of the integers, minus A, which is, all right, all this stuff, subtract, pick out all these things. What's left? Well, it's just the numbers that weren't in A. So it's it's all the 1, 2, 3, all the way to 10, right? So that's the complement of A. You need the universe specified to understand what the complement means, okay? It's like everything that wasn't in A, but it had to have been in the universe still, okay? So again, a little vague. The universe will usually be given to you right now, but eventually you'll be able to understand it from context, okay? So, okay, once you've specified a universe, you can do a bunch of set identities, all right? So this is very, very similar to your logic rules. It'll look exactly the same as your logic rules, in fact. So the set identities will look very, very familiar. Here's a list of them. Do you see how similar they look to some things that you've learned before? So we'll get to them in just a second. But like, for example, there's a De Morgan's law. There's De Morgan's law for sets. The complement of A union B is the complement of each set, and flip the union to an intersection. The complement of A intersect B all at once is complement the two sets and take their union. Oh man, does that make sense? So let's prove one of them. So that this is true, right? The complement of A union B, that's equal to, just take the individual set complements and intersect them, all right? This looks a whole lot like complement being negation and union being or and intersection being and that is very true, all right? So the reason this is true and works is because the set operations are defined using logic, all right? So let's figure this out together. Okay, let's prove the first De Morgan's law. So the way that you prove that two sets are equal is you just prove, right? Let me go back to this. You just prove that this is true. If X is in the first set, it's in the first set if and only it's in the other set. Okay, so that's one way to prove that two sets are equal. We talked about that, so let's use that idea, all right? So if I have an X in A union B bar, I better have a bunch of chains of if and only ifs eventually showing that X was also in A bar intersect B bar. That's how I'll prove them equal. So if X was here, it's totally here, and vice versa, because it's a biconditional. It goes both ways. So that's where I'm going with this. All right, I'm trying to prove all that. So if I know this, what do I know? Let me translate it to logic. What does it mean for X to be in a complement? All right, if X is in the complement of A union B, where is that? That means X was in X was in the universe. X was not in the original set A. Okay, does that make sense? So that's the idea. So X was not in the original set A. And by the way, if you say that X was not in A, or sorry, let me write it this way. If X was not in A, that's equivalent, right, logically to the negation of X being in A. And that's that we kind of want it like that because we know more stuff about in rather than not in. So if x was in the complement of A union B, that means x was not in A union B. Alternatively, it's not true that x was in A union B. So let me write that. If and only, this is also equivalent, right? It's not true that x was in A union B. And now, what does it mean for x to be in a union? Dun, dun, dun. So that's true if and only if. What does it mean for x to be in the union of A union B? Let's keep the negation outside for a second. Well, x is in a union if x is in A or x was in B, in either one. So there's the or coming in. Dun, dun, dun. So again, we keep this negation along for the ride, but let's expand the x in a union to be, all right, either x was in A, it's not true that x was in A, or x is in B, right? Because that's the expansion of the definition of union. Cool, that becomes this. Then we still have the negation along for the ride. And now I can push the negation inside, and it becomes a normal logical De Morgan's rule application. Isn't that fun? So let's do that. Let's push it inside. I don't know the best way to draw this so that you can understand everything still. We're pushing that inside right now. And that becomes, well, not x in A and not x in B. You see that? That's pretty nice. Let's see here. And you know that the not in has a whole lot to do with complements, right? If something's not in something, it means it was a complement. So that's the definition. Just we're running the definition of complement backwards. So if that's true, then x was, if it's not true that x was in A, then it must have been in the complement of A. See that? Assuming we've defined a universe. And x was in the complement of B, if it wasn't in B. Complement of B. So we got both of those now. Let's see, what else? And what do we know about that? So now we have an and. X was in the complement of A and x was in the complement of B. What set theory idea is defined using and? It's intersection. If you have an intersection, you can make, if you have an and, you can make an intersection. That's what's going on there. So all right, that means x is in, boop, A bar intersect B bar. And that's what we wanted to prove. Every time it's in here, and vice versa, because it's biconditional, if and only if. So therefore, we've proven that everything's in one is in the other, and vice versa. Therefore, A union B complement is equal to A complement intersect B complement. And that follows from the way it was defined using logic. All right. So every one of these laws that looks very similar to the ones you know, like double complement, double negation, associativity, distributivity, all those fun things, commutativity, they're all following from the idea that you're defining this using logic, just like underlining the definitions, expand them all, you make logic, then you prove it using logic. All right. And like the empty set functions in set theory as false, essentially. Like it provides nothing. And then the universal set functions as truth, like it's everything all at once. It's what you want. Okay? That's what's going on there, and that's why this works. All right, so here's one example for you. So here's this guy. Now just like pause and look at this table and prove that this is equivalent, it's equal to the empty set. All right? And use every identity, name everyone as you use it, so make a little table. So here's your table, pause this, look at this, and then write a table that tells, like, lists all your steps in every rule that you use. All right, so we're starting from here, right? A intersect B complement. We're trying to prove that that's equal to the empty set, so we're starting here. And then, all right, what do we know from here? Well, B intersected with its complement, there's a rule for that, right? Anything intersected with its complement should be false. Where is that? Because, there it is. Anything intersected with its complement. So like this is all of the things in A, and this is all the things that are not in A. They share nothing, and so their intersection is the empty set. So this becomes A intersect empty set using one of the complement laws. Complement law. And then anything intersected with the empty set, just like pick out all the things they share. They share nothing. They share emptiness. So this becomes the empty set using the domination law. So it's like false. You're ending with false, essentially. That's legitimately what's happening in the logic land when you expand the definitions. Domination law. Cool. So you got that. So all those rules are fun. All right, of course, there's more definitions. You can't escape them. There's so much to set theory. I'm sorry, but you'll be reading about it too. You'll be trying them all out in your homework as well. So I believe in you. We can do it together. So let's talk about a new idea called Cartesian products. All right. So this is when you want to just like specify that you have pairs of things, and it's ordered pairs of things, by the way. An ordered pair of values looks like this. It's like in parentheses a comma b. Okay. It's like a set of coordinates, or like a pair of coordinates, like you're graphing in 2 dimensions. So an ordered pair, like everybody wanted this stuff to be defined in terms of set theory, and so here's what they came up with. Let's define this pair, AB, to be a set, right? Because we want everything to be defined in terms of set theory. We can't just say like this, the ordered pair AB is equal to the set AB, because order doesn't matter in set theory, because like the set AB is equivalent, it's equal to the set BA. So we can't do that. So we need a way of specifying that A comes before B, but writing it in sets somehow at the end of the day. So let's define the ordered pair A comma B in that order to be this set. The set containing A and the set containing AB. All right. So if you define it in this weird way, you know which one comes first, because the size 1 set tells you the thing that came first, and then you take that out of the other one, and that's your second thing. Isn't that weird? But I mean, that's one way you can define it using sets and make it non-ambiguous which one comes first. So there you go. And that's an ordered pair. And then you can talk about a bunch of sets of pairs. All right, and that's called a Cartesian product. All right, the Cartesian product, it was ordered pairs, by the way, come from René Descartes, and so that's why we call it Cartesian product of the sets A and B. That's the set of every ordered pair in which the first thing was in A, the first entry was in A, and then the second entry is in B. All right, and we write it as A cross B, the Cartesian product of A and B. Okay, so for example, let's try and make this concrete. If A is the set 1, 2, and B is the set A, B, C, what is the set A cross B? That's the Cartesian product of A and B. It's all the pairs where the first thing's in this and the second thing's in this. All right. So what are all of your options? A cross B. The set of all the pairs where you take the first thing from this guy and the second thing from this guy. Well, all right. You can take the 1 and pair it with the A, of course. Alternatively, you can still take the 1 and pair it with the B. You can have 1B, 1C. See that? Or you can take the 2, and I can start taking 2s, pair them with the A. 2, pair it with the B. 2, pair it with the C. Or you take 3s, 3, pair it with the A. 3, pair it with the B. And 3, pair it with the C. All right? And that is your Cartesian product. That's the set of all the pairs that you can make with the first thing in A and the second thing in B. That's A cross B. And remember, that's ordered. 1 comma A is not the same as A comma 1. Very important. So, yeah, that's what's going on there. And the cross has to do with cardinality as well. Like the cardinality of A cross B is just the size of A multiplied by the size of B. You see that? Because like you got 2 things here, 3 things here. All the pairs you can make is you got 6 of them. Or sorry, did I do that right? 2, 3. Oh, I'm silly. Excuse me. You must have been yelling at your screen this whole time. Yeah, there should be 6 things in here. There is no 3 in A. I like the set 1, 2, 3. I got carried away. So excuse me. I'm sure you were yelling at me before, but now we got it. That's the set. There are 6 things really. I was just hallucinating the 3rd thing. Sorry. It's like you pick that one, and then you can have A, B, and C, or you pick this one, and then you have A, B, and C. There was no 3 in A. I'm so sorry. But that's the idea, right? There's 6 things in this set. So, yeah, that's where I wanted to go with that. That's Cartesian products. And, of course, you can product together many, many things. You can product together more than 2 sets. You can make not just pairs of things, you can make triples of things. You can have ordered triples that look like this, A, B, C. They come from Cartesian products of 3 things. Like, all right, you got A, and B and C. Oh, and by the way, like if you had a like you were graphing stuff on like a graph, like you wanted to plot this coordinate would be an ordered pair that was in like this was like, I don't know, 2, 3. 2, 3 would be in like all of your ordered pairs would be in like the set R cross R, because like you could have any real numbered x coordinate and any real numbered y coordinate. All right, that was just an aside. That's the usual thing you do when you're graphing. Okay, so you can make triples, you can make quadruples, but people like to call them n tuples, like to generalize it, and so that just like generalizes the idea of having a Cartesian product of multiple sets. So for example, you can have this set, you can cross it with this set, you can cross it with this set, cross it with this set, and so it's like, all right, you could take a 2 from the first one, take an A from the second one, take a B from the third one, take a 7 from the last one. It's like, because there was the 2 here, the A here, the B here, the 7 here. So it's just like there's an ordered quadruple, okay? And people sometimes call this 4 tuples instead, making it easier to just generalize the idea. And there is also a war between people who think that this is pronounced tuple and people who think it's pronounced tuple. All right, so we would call this guy a 4 tuple. I guess you can call it a quadruple if you want to, but I'll call it a 4 tuple, and that's the idea. All right, so that was a 4 tuple. An alternative 4 tuple is let's see. Let's draw it this way. You can have, I don't know, you can pick 1 this time, you can pick B this time, and then C, and then 8. That's another element. I'm doing it backwards, right? It's another element of that Cartesian product, 4 tuple. So tuple, it's silly I have to say this, but there is a war, and I'm going to have you pick a side right now. Tuple is pronounced, there's a whole Stack Exchange page about it. Tuple is pronounced, this is how I learned it. I'll say tuple, pronounced tuple, or alternatively, some people say tuple. Tuple. I say it this way. That's the way I learned it. That's the way my computer science professor said it. So pick which way you want, but I'll call it this is a 4 tuple, a 5 tuple if it was a bigger one, for example. So yeah, you can do multiple Cartesian products and take pieces of things. So like all the elements, like pick an A, pick a B, pick a C, and it's like a triple of things in that order. Okay, so that's that one. Now you try. All right, so here are 3 sets, A, B, and C. They hold these elements. Please write A cross B union A cross C using n tuple notation, and then there's also something called string notation. So I want to talk about that before I let you do this. So the last piece of this slide is string notation, and now I have a reason to teach it to you. So instead of just like writing out a bunch of ordered pairs, instead of putting commas in things, you can just skip the commas and say like you're making words, I guess, and this is your alphabet. And so you can just say 2AB7 instead of this, and that's like an alternative way of writing a very long tuple of many things. It's implied that every character is from an individual set. All right, so that's pretty nice. You have options. So I want you to use those options. Use this as like the normal Cartesian product notation with the ordered stuff, ordered n tuple, and then there's also string notation. So I want you to try both, please. All right. So write A cross B union A cross C using each of those styles. Then also see if you can figure out what B squared must be. All right. And Cartesian products is where we're going with this, of course. So see if you can figure out what the squared must mean. All right, so give that a try. So first of all, for A, what is A cross B and what is A cross C? A cross B, A cross C, what are those sets? So it's a set of ordered pairs where the first thing is an A and there's only an A and A, so there's only going to be one element. It's A, or only one element from on this side. It's always going to be an A on the left. And then what's B, B, and C? So you could have picked B for the thing on the right, and you could have picked C for the thing on the right, but A is the only thing that could ever appear on the left. All right. And then A cross C is, well, again, A, and then AA, AB, and AD. See that? A comma A comma B, and then A comma D. There we go. There's those. And so, all right, what's the union of these guys? The union of both of those. You got your, well, Well, AA is in there. I'll try to do it in some sort of alphabetical order. AA, AB, AC, and AD. That's just the normal n-tuple notation of like ordered pairs of stuff. And then if you wanted to do set or string notation, instead of writing it like this, these pairs, you can just plop the characters next to each other. You can be like AA, AB, AC, AD. Yeah, that's the idea there. And then B squared, did you figure that out? Well, what's a squared but a thing times itself? It's B cross B, it's the Cartesian product. All right, B squared is equal to, that's equal to B cross B, which is, well, just take the first element from B and the second element from B. So it's going to be, dun dun dun. Well, take a B first and a B first. It's like BB, BC. Then you can have like CB and CC. See that? It's totally fine, totally allowable to have like each of them coming from the same set. It's totally fine. And then again, that cross, it really is multiplication, just as you would understand it when you're using like finite sets and cardinality. So what's the size of B cross B? It's going to be equal to the size of B times the size of B. That's how many pairs you can make. That's pretty cool. Okay, so with that, let me have you prove something now. Let's keep our proof skills from getting rusty. So here are some definitions, all right? I hope they make enough sense to you. You've seen some of these before already. But use these 3 definitions down here, and then just the normal laws of logic to show that this is equal to this, right? These 2 sets are the same. So again, you're going to have like, you're going to have to use elements and things and show that the sets are the same using elements like I was doing up here. You have to kind of do it like this, start here, end here, with biconditionals all the way. But using that idea, see if you can figure this out. All right, prove that A cross B intersect C is equal to A cross B intersect A cross C, right? And so you'll use the definition of set intersection. It involves an and, union involves an or, and then the new one is Cartesian product. Here's the definition of Cartesian product. X comma Y is in one set A cross B if and only if the X was in the A and the Y was in the B. See that? So let me start you off. So you have A cross on the left, A cross B intersect C. So you have 2 elements, right? You have an element from here and an element from here. So you must have that X comma Y, that's where you start, is in A cross B intersect C. Then unpack that definition using the definition of, or unpack this idea using the definition of Cartesian product, and see if that'll get you closer to looking at making it look like this and saying that XY was in this big thing. Okay? That's where we're going. So give that a try, and then I'll show you my answer after you've finished. All right, so we got, all right, what is this? What is true about all this? Well, let's unpack the definition of Cartesian product. Well, we know that XY looks like this if the X was in the A part and the Y was in B, that's a bad element of symbol, B intersect C. Can't talk and write at the same time. There we go. So we got that. All right, and this is true if and only if. Let's unpack the definition of intersection. Let's get all the way to logic, as far to logic as we can. So Y is in B intersect C. So I got the X in A along for the right, of course. And then and Y is in B intersect C if Y was in B or Y was in the C. Oh, sorry, Y was in B and Y was in C. Excuse me, it's intersection. My bad, my bad. So, and you don't, like, that's associative because we just got a bunch of and. So Y is in B and Y is in C. It's got to be in both of them at once to be the intersection. And so now I have all this. And now I can start doing rules of logic because I want it to start looking like this, right? So I got to get like an A over here and a B over here and like an A and a C. So I kind of have to duplicate this A, and that's totally fine. There's a rule of logic that you can just like and together a bunch of A's at once. So like let's bring another A into the mix. X in A and X in B, and let's bring another X in A. It doesn't matter, you can have it twice. And Y. No, sorry, it was Y in B originally. That was a Y in B. Oh no, what happened? Sometimes the erasing just doesn't work and I don't know why. So let me just rewrite it anyway. No, everything's not working. That's really weird. All right. We can somehow fix this still. There. So we had it was y and b, excuse me. Y and b. And then let's bring another x and a. That's totally allowable. You can have it twice. And y and c. Okay? And where I'm going with this is I want to draw parentheses like this. A bunch of ands is associative, so I can draw parentheses wherever I want. That's totally fine. And now this looks a whole lot like a Cartesian product. Do you see that? That's pretty nice. So this is in, all right, you have this expands or unexpands. It's like you run it backwards to say that x comma y is in A cross B, right? That one is x comma y is in A cross B. And then this one is x comma y is in A cross C. Cartesian product with C, A and C. Okay, that's true if and only if. You have an and. This is an and, not an intersection. Let me try and, oh no, the erasing wasn't working, so let's see. Okay, now it's happy for some reason. That's an and, sharp. And so the and, you can unfold that back into an intersection. So this is like x comma y is in A cross B intersection with A cross C. And so every time you have this guy over here, you have this guy over here too, and vice versa. So we did it. We proved equality. So therefore, what we wanted is true. What we wanted was, we know that A cross B intersect C, that is equal to, whatever that was, it was equal to the same set over here written differently. A cross B intersected with A cross C. Okay? That's the idea. So that's what's going on there. And yeah, I hope that makes some sense. Let me write these a little bit better here. A cross C. So that was a nice equivalence proof, equality on sets proof. Okay, so let's see, where do we want to go next? Let's next talk about strings. Let's talk about strings, and let me say it this way. So again, we were talking about the notation for them. So we had this guy. You can do it like this. This is totally fine. To AB7 instead of like this. So strings are really just ordered pairs, really long n tuples usually. All right, so that's why we're talking about them here. So an n tuple of characters is just a string. All right, and so if a string S is an element of a to the nth power, right? So it's like A is all the characters you can use, right? And you have n characters in your string, and S is an element of that. It must be an n-sized thing, where each character is from A, this set A. We call A the alphabet, which makes a lot of sense, right? Because A is the set of characters you're allowed to use. Whee! So set of chars you can use. That's the idea there. So that's what's going on. And how do I want to do this? So yeah, if this is your alphabet A, right? Define it to be all the letters A through Z lowercase. Then the string hi mom is in A to the 5th power, right? It's an A cross A cross A cross A cross A, right? A 5 times, because there's 5 characters. It's a string of length 5. You see how that works? You've taken something from A 5 times. So it's like an ordered pair. It's a 5 tuple, but we're using string notation, all right? So because strings are secretly ordered things, ordered pairs, ordered n tuples, that means strings are also secretly sets. We're going to use that weird notation for them that looks like this. Where was it? This guy. You can expand that. You can extrapolate. Here it is. It's disgusting, but all right. The string ABCD defined to be the ordered 4 tuple A comma B comma C comma D, which is defined to be this. Disgusting. But it's just like it's building on top of itself. It's just a bunch of pairs together, okay? Because you can think of it that way. You can think of A comma B comma C comma D, and this is what the mathematicians did anyway. That's equal to this, like do the C comma D and then put like a B out in front. It's just a bunch of pairs at the end of the day. You can think of it that way, and that's how you come up with the definition in terms of sets. All right, so everything's building on top of itself, and that's kind of fun. That's kind of cool. Okay, So yeah, we're learning string theory in these slides because it makes sense. It's really sets at the end of the day. We can define strings in terms of sets. So some strings that we care about are binary strings. That's where the alphabet is 0 and 1. So for example, this binary number 101010, that's a binary string of length 6. So it's in 0, 1, that's the alphabet. And there's 6 elements, there's 6 letters in this one. So it's 0, 1 to the 6th power, right? Because it's a size 6 binary string. So this is a binary string. Okay. There's also the concept of the empty string. It's just the single string that you could write that's empty, whose length is 0. All right. So it's called like 2 quotes, right, in C++. And it's lambda. Lambda is like the Greek L. And so I think that, I had to look this up, but people assume that it comes from the German leer, which means, it's also a Spanish word, but in German this means empty or blank, which makes sense, I guess. And so that's a string thing. There's also the concatenation of strings, which I'm sure you've seen before. It's just the plus operation in C++. Like the concatenation of these two strings, 101 and 010, is the string. You can write it like this. You can write it st, and that implies that you're taking those characters and putting them next to each other. You're taking the 101, 010, and plopping them right next to each other. Okay. So that's the concatenation of the strings. And then concatenating with a lambda with the empty string on either side just doesn't do anything because you're not adding any characters. All right. So for example, A, B, C plus D, E, F in like C++ land creates the string A, B, C, D, E, F. This is the same idea but in math. Okay. That's where we're going with that. And that's like the same idea with the empty string. A, B, C plus the empty string in C++, or sorry, the empty string still is ABC. Okay, so it's what you know and love. We're just doing math with it now. We can, and eventually we'll prove stuff about it. And then the empty string does nothing, like hi, lambda, m, lambda, o, lambda, lambda, m. That's still equal to the string hi, mom. See that? So that's the idea. That's where we're going. Let's see. Not too much left for the day. Let's talk about now partitions. All right, we can partition sets. So, two sets, A and B, we call them disjoint. That's like they're separate, right? They're disjoint if they don't share any elements. And a way to write that in math is, of course, using some set notation. Like, all right, they're disjoint and they don't share anything. That means their intersection is nothing. Intersection is empty, all right? So, for example, two disjoint sets are like, let's say that A is the set 1, 2, 3. And B is the set 4, 5, 6. These are disjoint sets because they don't share anything. And you can discover that with a proof by just like intersecting them and noticing that you get empty set, right? You can also have a sequence of sets and call them pairwise disjoint if every possible pair of those sets are themselves disjoint with one another. And so these don't share any elements at all among any combination of them. So the way this bunch of these sets, A1 through AN, they're pairwise disjoint if for every one of them, if like every separate pair, AI and AJ, for every possible I and J that aren't the same, they're disjoint themselves. So their intersection is empty. So these are all pairwise disjoint. If any pair of them, any combination of them, any AI and AJ, they're always disjoint as long as they're not the same. Okay? So that's pairwise disjointness. That's useful to have. And a bunch of pairwise disjoint sets, we say, can partition an original larger set, S. All right, so a partition of a set is a collection of non-empty subsets, so smaller sets inside, that like together make up. Each element of S is in exactly one of the subsets. They make up the set S. It's like you're just partitioning it. You're dividing it into a bunch of pieces. So, all right. So, for example, let's use some fancy math. So, the sets, the smaller sets A1, A2, all the way to AN, they're a partition of a bigger set S, if and only if they're all subsets. Every AI, like it's a subset of S. They're all non-empty, because otherwise, like, why would you have that one? Like, they're all non-empty. They're all contributing something. They're all pairwise disjoint. You're not duplicating. You're not double counting anything. And then, together, they make up the original set. All right? So, for example, here's a set C. Let's partition it. All right, let's come up with let's make a partition that is 3 subsets big of this original set C of animals. All right, so let's say let's partition it maybe this way. And so in graphical form, it makes a lot of sense. Like here's a partitioning of the set. Like here's a subset, here's a subset, here's a subset. Those make a partition because none of them are empty, and all this other stuff is true. All right, so like let's make this. This can be A1, this can be A2, and this can be A3. That's the idea. And so A1, define that to be, I don't know, koala and squirrel. All right, and then A2, define that to be raccoon and cat. And then A3, define that to be dog, the set containing dog. And we can prove to ourselves, like, this is a partition because these are all subsets of the original set C. They're all non-empty. They're all pairwise disjoint. They don't have anything in common, right, with one another. And then together, union them all together, they make up the whole set, all right? And so it's just like you're drawing some lines between things. That's really a partition. That's what it means. It's just we're mathematically specifying that. There's a reason for it. We're going somewhere eventually, okay? So that's partitioning, and yeah, let's use that. Here's an example. So you try this. So let's define the sets A, B, C, and D like this, just a bunch of numbers, all right? So think about it. These are real subsets of the real numbers. So A is like every real number that's strictly smaller than -2. B is all the real numbers that are strictly bigger than +2, or yeah, strictly bigger than +2. And then C and D, I want you to figure it out involving the absolute value notation. I would like you to figure out, first of all, do these sets, A, B, and let's say A, B, and C, do they form a partition of R? And then think about A, B, and D. Do those form a partition of the real numbers R? Okay, just like every number. So here are the 4 requirements for a partition. So remember those, and then give that a try. All right. First of all, do the sets A, B, and C form a partition of R? So one big thing about them is together they need to make up the whole thing, right? That's a big thing about partitioning. So let's just make sure that's true. So all right, do the sets A, B, and C form a partition of R? So let's think about A, B, and C, and like the real numbers is like the number line. It's like here's the number 0. We got some -2s and 2s involved, so let me draw that. So A contributes, if we're trying to union these all together, make sure they like form all of R. So A is everything strictly smaller than -2. So A covers all that. And then B covers everything bigger than 2. Boop. But not 2 itself. Whee! Covers everything bigger than 2. That's B. And then C, it's all the numbers such that their absolute value is strictly smaller than 2. So it's like 1.9999. Everything over here, because its absolute value is smaller than 2. Everything over here, because its absolute value is smaller than 2 as well. It's already positive. But, so that's C altogether there. All the stuff in the middle. But do you see how they missed out on exactly being -2 and +2? All these never actually hit -2 and +2, so they can't partition it. You see that? No. No is the answer there. A, union them together, that's a big requirement. A union B union C misses the set -2 and 2. So just 2 tiny numbers, but they're important numbers. They don't make all of R. What about A, B, and D? Do you see how D really does take the -2? It really does take the +2 because it's less than or equal to. So this is your D right here. So that one seems to at least work for that part, but we need to check them all. All right. So first of all, they union together. That was one thing we need to check. A union B union D. Do you see how that does create all of R? That's equal to R. What else did we need to check? Let's do it in order from then on. Are they all strict subsets of R? Yeah, they're all subsets of R. They're all just pieces of the real numbers. There's nothing extra there. No imaginary numbers. They're all non-empty, right? Each of them, A, B, and D, are all non-empty. And then the last requirement, the fourth requirement, is that they needed to be pairwise disjoint. So do A, B, and D, any combination of two of them, did they share anything? Like A, B, and D? No, it looks like they always hit separate numbers. They have nothing in common, which is perfect. So they don't share elements. So there's always, you can always talk about which partition a certain number is in. It's always well defined. That's important. All right? And so they all check off, and so the answer is yes. Isn't that beautiful? So they all form partitions, and there's always the concept of like which one is it a part of, okay? And so that's pretty nice, and this will come up later. We'll talk about like, there's a concept of like equivalence classes. That's a word that you'll be very, very familiar with later in the class, all right? So with that, a lot of what we've been talking about, like strings and stuff and sets and stuff, they exist in programming. For example, you have the set type in C++. That is defined to be a set of stuff. Here, let's go to the documentation for sets. Why not? While I start up my virtual machine, actually, because I have an example for you. Let me show you this. So, boop. And so while this is starting up, it has to just appear really quick. There it goes. There it goes. And then, so here is the sets type. You can do a lot of stuff to sets. You can insert stuff, you can take them out, you can get the cardinality of your set, you can iterate through it, you can check if something's there by seeing if it's in there with a find operation. So like sets make sense, right? You've already used them. A set in C++ is a balanced binary search tree, and so you have to worry about, because this isn't math, you have to worry about efficiency. So you get a logarithmic time lookup for sets in programming land, the set type. You also have an unordered set type. That is this one. And that has to do, that's the underlying version of that is a hash table. So you have a constant time lookup for that in the average case. So that is your C++ versions of sets. And of course you can do all the same stuff, essentially, that you were doing with the set type. You can just like check if something's there. You can union two sets together. You now know, you know the terms now. See if something's an element, not an element. Another thing you can do is what's called a formalization of sets. Okay? So let's talk about that. You can formalize sets. And what a formalization is it's when you implement the ideas behind sets, like unions, intersections, and stuff like that. But it's just, it's code that's meant to be easy to understand. It's not meant to be efficient at all. It's just meant to be like, all right, this is what it means. It's very clear what it means. All right? It doesn't have to be fast. It can be very, very slow. And so let's model sets and unions and intersections in Racket. So I've done that for us. Let me connect really quick. Whee! And let me do S24, go from class 26. S23, code from class 26, lecture 8. And so here is an example file in Racket that formalizes sets. So let's model sets as lists. Let's start with that. Let's pretend that sets are lists. And then I am going to model unions and intersections on sets. And so here's code. I've made some sets using like a make set helper function, and then I'll talk about all this code down here. So, all right, first of all, we need some helper ideas because sets can't have duplicates. So let's make sure to remove all the duplicates when I'm representing sets inside of a program. And then I also want a helper function that checks if something's in something else, because like that's how you get intersections and unions. Like it's got to be in both, it's got to be in either, stuff like that. So you need another helper to understand what it means to be inside of stuff. Here's a function that removes the duplicates, because we're going to model sets as lists. We're going to pass a list here, have it be converted into a duplicate list set of things. This is a function that I believe that you could figure it out. Let's see here. It's a recursive function, of course, because Racket, and this is a class that's big on proven stuff, so try to prove to yourself that the recursion's working. So for example, if I call remove duplicates on this list with all these things, it'll give back the list 1, 2, 3. And so the remove duplicates function works like this. Well, there's two cases, first of all. Like if you give an empty list, just give back the empty list. Empty lists don't have duplicates, you're done. Otherwise, if the list was non-empty, split it up into the first element and then the rest of the list. All right, first element and then the rest of the list. And here's what you do. All right, so let's recursively filter the rest of the list. Like we have this smaller list here. And what you do there is, well, this is like your first element, like it was your 1 or it was your 2. You can remove every element, every time first appeared in the rest of the list, like get rid of it. And that would have gotten all the duplicates of first out of the rest of the list. Do you see that? Like the filtered rest. So we're filtering with a lambda function that like picks out all the things that are not equal to x, all right, in the rest. And so that's your filtered rest. And so that's, you've taken care of getting the 1, for example, out of the rest of the list if it was there. And now go and recursively remove the duplicates of everything else in the rest of the list, and then plop the first at the front. Cons creates a list with 1 element and then a smaller list. So the final answer is that first element plus that filtered smaller list that's been recursively had its own duplicates removed. And so hopefully you can kind of understand that. I'm not like going to test you on that or anything. That's the idea. And so to make a set and model sets as lists, it's just like get all the duplicates out of there. So for example, L1, L and L2, here they are. I'll make the sets A and B out of them. And we're going to end up with 1, 2, 3, and 2, 3, 4. See that? So here I am printing them out. And then here's what it means to be an element of. You can actually use Unicode characters as function names in Rack. It's really cool because like the only real requirement is to use parentheses everywhere. Like every other name, you can have question marks in your name and weird symbols in your name. It's totally fine. So define element operation. X is an element of X, S. So we'll have this return true if X is an element of S. So like element XS is kind of how you're saying it. And like there's a member function on lists. All right. So if X is a member of the list S, just give back true, otherwise give back false. So that's how that one works. So checking if 1 is an A, that's true. Checking if 1 is in B, that's false, right? Because B doesn't have a 1. And then the union is pretty much like take the two lists, like we're modeling the idea of sets, right? We're modeling the idea of sets in code. It's just a reference implementation. We have to, like if we're choosing lists, we can use list operations, and as long as we make a normal looking set at the end of the day. So to union together two things, S1 and S2, two sets, you just like put the lists together, because that's how we're representing them, and then remove any duplicates that you had. Right? So for example, if you union A and B, it's going to be 1, 2, 3, and 4, because like you got some duplicates, but we're going to remove them. See that? So that just remove the duplicates after appending the lists to each other. That's pretty nice. Just combine them, remove the duplicates. And then here's intersection. All right? Here's intersection. So the intersection of two things is like it's got to be in both, right? To be in the intersection. So eventually we're going to make a set and we're going to remove the duplicates. But first of all, I need every element. All right? Let's get every element by taking the union of S1 and S2. Now I know what every element is that could possibly appear in S1 and S2. And then let's make a little helper function, or a helper idea is in both, right? Let's figure out all of the helper variable, I guess. Let's get all the elements that are in both sets. So I'm taking every element that was in S1 and S2 together, their union, and I'm filtering out the ones that were in both X1 and S2. Sorry, S1 and S2. So I'm filtering all of the X's such that X was in S1 and X was in S2 at the same time. So that's the logical definition of intersection, right? So I'm picking out every possible element that holds true for this, and then I know that it's in both if it gives back true, and so it's picking out all the things that are in both, and I actually think the remove duplicates is unnecessary since the union is already doing that, but who cares? Just for good measure, we're removing the duplicates from the in both lists that we're computing there. And so that produces 2, 3. And so do you see how I'm modeling in code? This is very inefficient. It has nothing to do with like hash tables or balanced binary trees, but it's much, much easier to read the implementation of, assuming like you're comfortable with Racket at least, right? So that is going to correctly give you the right thing. And so it's kind of easy to like read off the fact that, oh yeah, that's what it means to be a union. I get it. I can maybe implement that more efficiently later. But this is a reference implementation. Like it's very clear like that it's this is what it means to be the intersections. It's in both. That's the key piece of that. And so it's very easy to understand it and see why it works, and there is use in that. And so that is the idea of sets in programming. You have them made efficiently for you in libraries, and also if you just like wanted a formalization where you could like maybe prove things about easier or understand them better, you can do a reference implementation as well. And so I encourage you to try that in C++. You can maybe like model sets as vectors, for example, or just like lists as well. And so with that, I think that's everything that I wanted to tell you about sets, at least for now, because of course all of mathematics is defined in terms of them, and so they're gonna plop up a whole lot more, but now you've seen an introduction to them at least, and so hopefully you're feeling a little bit more confident about them. I'll of course give you homework about this stuff to drive the ideas into your mind, but yeah, that's all I've got for you, so please yell at me if you have any questions.